I want you to picture a single server rack. You've seen them in data centers, just a black metal cabinet, maybe the size of a fridge. Now, imagine that one cabinet has more bandwidth than the entire internet.
It sounds like, something out of science fiction, pure hyperbole. But as of this week, specifically between January 4th and January 11th, that idea, well, it became an engineering reality.
Welcome back to the deep dive. We're digging into a massive news dump out of CES 2026 in Las Vegas. But we're not talking about smart toasters today. We are focusing only on NVIDIA. Because it seems like while everyone else was showing off gadgets, NVIDIA just announced that the way we've been doing AI for the last few years is, it's basically over.
Over might be a strong word, but we are definitely turning a major page. For the last, 3 or 4 years, we've lived in the era of digital AI. Think chatbots, image generators, things that live on a screen. This week, NVIDIA signaled the official start of physical AI.
Physical AI, so taking the brain and giving it a body.
Exactly. We're talking about intelligence that can perceive, plan, and then act in the real world. But to do that, they couldn't just release a slightly faster chip. They unveiled a whole new computing architecture. It's called Rubin.
And that's our mission today. We're going to unpack this Rubin platform because the specs are, frankly, a little hard to wrap your head around. We'll look at why token cost is suddenly the only metric that matters and explore how AI is learning to drive cars and work in factories with something that looks a lot like human reasoning.
It's a very dense week. The implications of what was announced in Vegas are going to ripple out for years to come.
So let's start with that, the physical AI. I feel like we've been promised self-driving cars and helpful robots for, a decade? And mostly what we have are robot vacuums that get stuck on the rug. What actually changed this week?
What changed is the software. The headline story here is a thing called Project Alpamayo. It's a family of open-source models built specifically for autonomous vehicles. The CEO, Jensen Huang, actually called this the ChatGPT moment for robots.
Okay, hold on. That phrase, ChatGPT moment, gets thrown around a lot. We've had self-driving tech for years. Waymo, Cruise, Tesla. Why is this the big moment?
It all comes down to how the car makes a decision. Until now, it's been mostly perception and rules. The car sees a red light, the code says stop. It sees a pedestrian, the code says yield. It's all reactive. Alpamayo introduces what's called chain of thought reasoning to the vehicle.
Chain of thought? You mean like the little internal monologue I have when I'm trying to decide if I can merge into traffic?
It's surprisingly similar, yes. The Alpamayo 1 model, and that's a big one, 10 billion parameters, it doesn't just react. It explains to itself why it's reacting. So, for example, let's say the car sees a horse-drawn carriage.
A horse carriage. Okay, that's a rare one, but I see your point.
Right. A standard system might just see obstacle and brake hard. Alpamayo can process a thought chain that goes something like, okay, I see a horse carriage. It's an animal, not a car. It moves slow, might get spooked. Therefore, I should not just brake, but slow down gradually and give it a really wide berth.
So it's simulating the consequences. That feels critical for all the weird stuff you see on the road, the edge cases.
The long tail events, exactly. The stuff you just can't program an if-then rule for. And to help with that, NVIDIA also released over 1,700 hours of driving data. They're open sourcing it so researchers can train models on all those bizarre, rare scenarios.
But doesn't all that thinking take time? If a kid runs out in front of my car, I don't want it having a philosophical debate. I just need it to slam on the brakes.
And that's the core tension. You need the reflex and the reasoning. And that also applies to robots, not just cars. Which brings us to their other big software release, the Cosmos and GR00T models.
GR00T, like the character from the movies.
It's spelled with 2 zeros, but yeah, that's the idea. GR00T N1.6 is for humanoid robot control. And Cosmos is what they call a world foundation model. Basically, think of it like a physics engine that lives inside the robot's head.
So if a robot picks up a glass, Cosmos is the part that instinctively knows if I squeeze too hard, this will shatter, and if I tilt it this way, liquid will spill.
Precisely. It builds an intuitive model of cause and effect, and that lets robots move from being single-task machines to generalist specialists. They can look at a messy factory floor and figure out how to clean it up without being explicitly programmed for every single object.
But here's the problem I see. Running a world model in a chain of thought process, that sounds incredibly expensive computationally. You can't have a robot towing a server rack behind it. It all has to run on the device, right? At the edge.
That is the big challenge of edge AI. And that's where the hardware news really comes in. Tucked away in all the announcements was the Jetson T4000.
Right, the Jetson. That's been their robotics chip for a while. So is this just a minor speed bump?
Not at all. It's a massive leap. It brings the Blackwell architecture, that's their current top-tier data center tech, down to the edge. We're talking 1,200 FP4 teraflops, 64 gigs of memory.
Okay, in English, please.
It's essentially a supercomputer that's about the size of a credit card. But the kicker is the price. At volume, it's around $1,999.
$2,000 for that kind of power. That's shockingly accessible for industrial hardware.
It's a game changer. It means you can put that agentic AI, the reasoning AI we were talking about, directly inside a delivery drone or a warehouse robot. You remove the latency. If a robot slips on a patch of oil, it needs to correct itself in milliseconds. You can't wait to ask a data center in another state for permission.
You know, it's interesting you mention accessibility because I saw it wasn't just for huge industrial clients. There was some news for the PC crowd, too. Is that just NVIDIA throwing a bone to gamers, or is there a bigger picture?
Oh, it definitely matters for the bigger picture. I mean, sure, they announced DLSS 4.5, which uses AI to hallucinate extra frames in video games to make them look smoother. But the real story is the democratization of the tools. They updated local AI libraries like llama.cpp and Llama to run up to 35% faster on consumer RTX PCs.
So the same kind of reasoning tech we were just talking about for robots in a factory is getting easier for anyone to run on their home computer.
Exactly. And that closes the loop. The developer who's inventing the next generation of robot brains can now prototype and test it on their own PC. The gap between consumer AI and enterprise AI is shrinking fast. And that accelerates the whole ecosystem.
All right, let's get to the main event. The Internet in a Rack you mentioned at the top, the Rubin Platform.
This is really the heart of it. In the past, NVIDIA would come out and show us a new GPU and say, hey, look, it's faster. Rubin is completely different. It's what they call extreme co-design.
Extreme co-design? That sounds like a bit of marketing jargon, or what does it actually mean?
It means the end of the modular server as we know it. You can't just swap out a part anymore. Rubin is 6 specific individual chips that are all designed to work as a single unified system, like an organism. Because if your GPU is incredibly fast when your networking is slow, the GPU just sits there waiting. If the CPU can't feed it data fast enough, the whole system just chokes. So they redesigned everything at once to eliminate every single bottleneck.
Okay, so let's break down this organism. What are the key parts?
Well, the heart is still the Rubin GPU. It's delivering around 50 petaflops of compute. But the real magic isn't just the raw power. It's a new type of math they're using called NVFP4.
NVFP4, so 4-bit floating point. I've heard people say that using 4-bit math is less precise. Why would we want AI to be less precise?
It's a great question. Think about catching a baseball. You don't calculate the exact arc and wind resistance to 10 decimal places.
Right, I just sort of get my glove in the right area.
Exactly. You'd use a good enough calculation. Neural networks are very similar. They don't need hyper-precision for every single calculation. By dropping to 4-bit math, the calculations get way, way simpler. That means they run exponentially faster and use a lot less memory.
So we're trading some unnecessary decimal points for a massive gain in speed.
Precisely. And to feed that beast, you need the Vera CPU. This is a big deal because it's a custom NVIDIA-designed processor. It's an ARM chip with 88 cores.
That feels like a real shot across the bow at Intel and AMD. It's NVIDIA saying we can do this ourselves now.
It's pure vertical integration. They control the entire stack. Then you have the nervous system, which is the NVLink 6 switch. This gives you 3.6 terabytes per second of bandwidth per GPU.
That's the number from the intro, the Internet in a Rack number.
That's the one. When you connect all these together, the chips communicate so fast that the software doesn't see 100 individual GPUs. It just sees one giant unified brain.
So what's the output of that brain? I mean, we usually talk about performance and TFLOPS or something, but this week, the term I kept hearing was token cost. Why is everyone suddenly an economist?
Because the job we're asking the AI to do has changed. We're moving into that agentic AI era. If you ask a chatbot a question, it gives you an answer. Maybe that's 100 tokens. It's cheap. But if you tell an AI agent, plan the entire supply chain for my new business, it has to think. It might simulate 1,000 different outcomes, critique its own work. It could generate millions of tokens in the background just to come up with one good plan.
Ah, I get it. So if the cost per token is high, that kind of deep thinking becomes astronomically expensive.
Exactly. It's not economically viable. The big promise of Rubin is a 10x reduction in the cost to generate an AI token compared to their last platform, Blackwell.
A 10x drop, that's not just an improvement, that's a deflationary shock to the system.
It completely flips the economics. It makes it possible to have AI agents running 24/7, constantly optimizing a factory, instead of just waiting for a human to type a question.
But there has to be a catch. We're making these AI brains bigger and faster, but we're also asking them to remember more. If an agent is working on a problem for a whole week, it has to remember what it did on Monday.
And that is the context problem. Which brings us to another one of the 6 chips, the BlueField-4 DPU.
A DPU, so a data processing unit.
Right. Here's the issue. The AI short-term memory, its context, it takes up a huge amount of space. It's called the KV cache. Storing that on the GPU's super-fast memory is incredibly wasteful. It's like trying to memorize the entire phone book while also trying to do complex calculus. You run out of mental bandwidth for the math.
So what does the BlueField chip do?
It's like an external hard drive for the AI's memory. NVIDIA introduced a platform called ICMS Inference Context Memory Storage, which runs on BlueField. It offloads all that memory, the KV cache, to a dedicated storage layer, so the GPU can focus purely on the thinking. And BlueField handles all the remembering.
And the result of that is?
A 5x boost in tokens per second. It allows these agents to have enormous context windows, long-term memory, without slowing down the whole system.
That feels essential for any real business use case. If you're a bank, you need the AI to remember 5 years of compliance reports, not just the last 5 minutes. But speaking of banks, putting this much intelligence at the core of a company sounds like a massive security risk.
It absolutely is. If you have one giant supercomputer running AI for HR, for R&D, and for sales all at the same time, you absolutely cannot have those data screens mixing.
You can't have the sales bot accidentally learning about some secret R&D project.
Exactly. So to solve that, they introduced ASTRIBRA. It stands for Advanced Secure Trusted Resource Architecture. It's a hardware-based root of trust.
Hardware-based. So it's not just software, it's physically built in.
Right. It guarantees tenant isolation at the silicon level.
Right.
It makes it physically impossible for the data from tenant A to be accessed by tenant B, even if there's a software bug. It's the kind of thing that lets a chief information officer actually sleep at night.
So let's make this real. We've talked chips, we've talked robots. Who is actually writing the checks for this stuff right now?
The partnership list they announced was long, but one number really stood out to me. $1 billion.
That's the Eli Lilly deal.
That's the Eli Lilly deal. They're building a co-innovation lab with NVIDIA, and they're using NVIDIA's BioNeMo framework to essentially merge silicon and biology to reinvent how drugs are discovered.
But haven't drug companies used supercomputers for ages? What's actually different here?
It's a shift from discovery to engineering. Traditionally, drug discovery is a lot of trial and error in a lab. With BioNeMo, they can simulate exactly how a potential drug molecule will interact with a protein inside the body before they ever make it in a lab.
So they can fail 1,000,000 times in the simulation for free instead of failing once in the lab for millions of dollars.
Exactly. It could dramatically shorten the timeline for developing new medicines. It's physical AI being applied to molecular biology.
And then on the total opposite end of the spectrum, heavy metal, Caterpillar.
Yes, Caterpillar is integrating Jetson Thor into their heavy machinery, like mining trucks and excavators.
Jetson Thor, is that different from the T4000 we mentioned earlier?
It's the higher-end, more rugged version for these huge autonomous machines. This is all about safety and efficiency. A mining site is a dangerous place. If you can have a physical AI moving dirt, reacting to changing terrain, and avoiding other vehicles without a human in the cab, you save lives.
And then you have Siemens doing a similar thing, but for factories.
Right, building what they call an industrial AI operating system. The goal there is what's called adaptive manufacturing. A factory that doesn't just stop when there's a supply chain problem. The AI just replans the entire production schedule on the fly and reconfigures the robots to keep everything moving.
It really does feel like the brain is finally getting connected to the hands.
That is the perfect way to summarize this entire week.
Okay, so let's wrap this up. We started with a server rack having more bandwidth than the whole internet. We talked about cars that reason, robots that understand physics, and a 10x drop in the cost of intelligence itself.
The through line for all of it is that pivot from digital to physical. The hardware Rubin is finally fast enough and cheap enough to support the software Alpamayo and Cosmos that lets AI actually leave the screen and interact with the world.
And I want to come back to that 10x cheaper point one last time, because that feels like the real lever that's going to move the world here.
There is.
You know, in the Industrial Revolution, machines made physical force cheap. You didn't
Yeah.
need 100 people, you needed one engine. In the information revolution, computers made calculation cheap. You didn't need 100 accountants, you needed one spreadsheet.
And
Now it seems NVIDIA is trying to make reasoning cheap.
and incredibly fast.
Right. So here's the question that I want to leave everyone with. What happens to our economy, to our jobs, to our daily lives when the cost of thinking through a very complex problem drops to nearly zero? When the bottleneck is no longer the brain power needed to find the solution, but just the battery life of the robot that's carrying it out?
That is the question that's going to define the next 10 years.
Something to chew on. Thanks for diving deep with us. We'll see you next time.